Hello everyone, welcome back to my YouTube channel. So today we are going to solve day 24 problem of this month on LeetCode. Before starting, if you guys haven't subscribed my YouTube channel yet, then please go ahead and subscribe it. Now without any delay, let's get started with today's problem. Problem number 2322. Minimum score after removals on a tree. Let's read the problem statement. There is an undirected connected tree with n nodes labeled from 0 to n-1 and n-1 edges. Okay, you are given a 0 indexed integer array nums of length n, where nums of I represents the value of the ith node. You are also given a 2D integer array edges of length n-1, where edges of I is equal to a to b, indicates that there is an edge between nodes A and B in the tree. Okay, so see this example number 1, nums. Alright, so what is the length of this nums? N value is equal to 1, 2, 3, 4, 5. Okay, so that simply means that we have nodes from 0 to 4. Okay, 0 to n-1, right? And how many edges we have? 4 only, n-1, right? So here you see 0, 1, 2, 3, 4, done. Okay, and how many edges we have? 4, right? 1, 2, 3 and 4. Okay, and here this 0 index, 1 index, 2 index, 3 index and 4 index. Okay, so for node 0 value is 1, for node 1 value is 5, for node 2 value is 5, for node 3 value is 4, and for node 4 value is 11. Okay, it's clear, right? And we have these edges as well. So 0 to 1 there is one edge. Okay, this is undirected graph. Okay, so 0 to 1 means 1 to 0 also there is one edge. Okay, so we have nodes like this 0, 1, 2, 3, 4. Okay, so 0 to 1 there is an edge, same way 1 to 0 also there is one edge, 1 to 2 there is one edge, same way 2 to 1 also there is one edge, 1 to 3 there is one edge. Okay, 1 to 3 there is one edge, same way 3 to 1 also there is one edge, right? Okay, here also you can see 1 to 3 or 3 to 1. Okay, and same way 3 to 4 there is one edge, so I can say 4 to 3 also there is one edge. Okay, so this is nothing but my adjacency list. Okay, so here I have created one adjacency list for this. Okay, so I hope that you guys are clear with this input. Okay, and how I'm creating this adjacency list, right? Done. Okay, now after that we have to remove two distinct edges of the tree to form three connected components. Okay, for a pair of removed edges the following steps are defined, right? So what we need to do, we need to get the XOR of all the values of the nodes for each of the three components respectively. The difference between the largest XOR value and the smallest XOR value is the score of the pair. Okay, so let's understand these two lines with an example here. Okay, for example, say the three components have the node values like this 4, 5, 7. Okay, 1, 9 and 3, 3, 3, right? The three XOR values are 4 XOR 5 XOR 7 is 6, 1 XOR 9 is 8, 3 XOR 3 XOR 3 is nothing but 3. Alright, the largest XOR value is 8 and the smallest XOR value is 3. The score is max minus min. Okay, so 8 minus 3 is equal to 5. So we have to return the minimum score of any possible pair of edges removal on the given tree. Okay, and you already know, right, XOR how we calculate. So if two values are same, result is always going to be 0. Okay, 1, 1, it is always going to be 0. Okay, and if one value is 0 and if one value is 1, then output is always going to be 1. Okay, so this is nothing but my XOR table. Okay, A, B, and this is my result. All right, so now here let me prove 5 4 XOR 5 XOR 7 is 6. Okay, you already know, but let's again let me explain. Okay, so how we write 4 in binary form? We write let's say this bit value is 1 2 4. Okay, so we write 4 like this 1 0 0. We write 5 like this 1 0 1. Okay, so if you do the XOR of these two, Okay, so 0 1 different, right? 1 0 0 same 0, 1 1 same 0. So this is nothing but 1 only, right? Now how you write 6 in binary form? 1 1 0. Okay, so now do this. Okay, do this XOR of this with this 6. Okay, so what is the output? You are going to get 1 0 different 1 0 1 different 1. Okay, this 0 1 different 1. Okay, so what is this 1 1 1? This is nothing but 7. That is why 4 XOR 5 XOR 7. Okay, it was 7 not 6. Okay, but 4 XOR 5 XOR 6 is equal to 7. All right. Okay, this is clear why we are getting 7. Okay, so now here is instead of 6, if you want to see this example only, we have 4 5 and 7. Okay, so let me just change it to 7. Okay, so now here if I write 7, so here 7 I'm going to write it like this. Okay, 1 1 1 and here also 1. So now what is the output you are going to get? Here you're going to get 1 1 and 1 1 same. Okay, 0. So then that means the output is 6. Okay, this is 6. So here 4 5 and 7. Okay, output is 6. All right, so now here if you notice one more thing, okay, here I was doing 4 XOR 5 XOR 6 and I was getting 7 as the output. Okay, so I can say this is nothing but my total value. Okay, total value, let's say. Okay, and let's say this is nothing but my A value. Okay, this, and let's say this is my B value, right? So now here uh, I can say that this is nothing but A XOR B is equal to total, right? A is this complete 4 XOR 5. Okay, B is nothing but 6 and 7. Okay, now here if I told you find out the value of B, okay, let's say I don't know the value of my B, okay, but I know the value of total and I know the value of A, then also it is very simple, right? What I need to do, I need to take A here, okay, and here I need to take the total. Okay, I will get B. Okay, so here I prove one more property of this XOR, right? So A XOR total, so I will get B. Okay, so that simply means that this is nothing but reversible. Okay, so if I know the total and if I know one part, I can definitely calculate the second part. Okay, so XOR property is nothing but, we call it reversible property. Okay, reversible property of XOR, right? So I proved that as well here. Okay, we will discuss this out later as well, but I hope that you guys are clear. Okay, this is done. Okay, so here now what we need to do, okay, so here we have one graph, right? We have one graph, right? So if I just remove this, then it is going to divide this into two graphs, okay, into two components. Okay, but if I cut two edges, then I will get the three components. Okay, so here in this example number one, if I just cut this and cut this, okay, if I don't use this, so this is one component. Okay, this is one component, so this two value is 5. Okay, the here second component has node 0. Okay, node 0 alone, right? So value is 1, so XOR value is 1 only. Same before this third component, let's say, okay, this is third, let's say this is second component, and this one is one first component. Okay, so third component is node 2 with the value 5, so its XOR value is 5. Okay, now first component is going to be 1 3 and 4. Okay, if I cut 0 and this these two edges, okay, red color edges, so 1 3 4, so 1 3 4 XOR value is 10. Okay, so 10 1 5, what is max? 10. And what is min? Okay, 1. Okay, so 10 minus 1 difference is 9. The score is the difference between the largest and smallest XOR value, which is 10 minus 1 9. Okay, so it can be shown that no other pair of removals. Okay, so this time you highlighted these two in red. Okay, next time maybe you mark, you cut this and cut this. Okay, so your choice. But as per example number one, if you are going to cut these two, you are going to get the best answer. Okay, so it can be shown that no other pair of removals will obtain a smaller score other than 9. Okay, so that is why 9 is output. So I hope that you guys are clear. Okay, same way for example number 2, if you cut these two, okay, so you are going to get two components or three components like this. Okay, this, right? So first component 3 4 with the values 4 and 4. Okay, these values we have to do the XOR of values. Okay, so XOR values 4 XOR 4 0. Second component is 1 0, okay, with values 5 5, this. Okay, third component this 0. Okay, so score is the difference between the largest and smallest, so 0 minus 0 0, that's it. Okay, so now let's see how we are going to solve this problem. Okay, how we are going to calculate. Okay, so how we are going to find the answers. Okay, how we are going to find out that this is the red and this is the red. Okay, note this one and note this one. Okay, which red is going to give the best answer? Let's find out how we are going to do that. Okay, so first okay, these are the constants, nums dot length. Okay, just go over this. These are the constants given to us. Okay, edges represents a valid tree. All right, so first property of XOR is reversible. Okay, I already proved that above, right? So if total XOR is equal to XOR of the entire tree, and we know the XOR of some subtree, we can easily compute the XOR of the remaining nodes. Okay, simple, right? And tree property, unique paths. Okay, so in a tree, every edge removal partitions node into distinct connected components, subtrees. Okay, removing two edges creates three components, which can either be disjoint subtrees, one subtree nested inside another. Okay, so what does this mean? We will discuss about these two terms in detail. Okay, so let's discuss these two terms, right? So tree property, unique paths. Okay, so a tree, what is tree? Is an acyclic connected graph. Removing one edge splits the tree into two components. The subtree below that edge, okay, be disjoint subtrees, okay, and one subtree nested inside another. That means, okay, so two parts. Okay, so removing one edge. Okay, so here I'm just talking about the removing one edge. Okay, so I have one tree, I just remove this one. Okay, so now I have two components. Okay, so removing one edge splits the tree into two components. Okay, one is the subtree below that edge and the rest of tree. Okay, this, right? And removing two edges split the tree into three components. Okay, and for this there are two possibilities. These are the two possibilities. Okay, right? Okay, so two possibilities when removing the two edges. One is disjoint subtrees. Okay, so what does this mean? Disjoint subtrees. Okay, all right, so disjoint subtrees means the two edge you cut are not on the same root to leaf path. Okay, so 0 is your root and this is your leaf. Okay, so the two edges that you are going to cut are not on the same root to leaf path. Okay, their resulting subtrees do not overlap, right? Okay, so that simply means that I can cut this edge, okay, and I can cut this edge. Okay, so here 0 to 2, this is another path. 0 to 3, this is another path. Okay, so cut edges 1 and 3 and 0 and 2. Okay, so subtree A is 3. Okay, this one only. Subtree B you can say 2, and you can easily calculate the value of this one. Okay, 0 1 4, right? Okay, remaining is 0 1 4, right? So this is done. Okay, so now here you can take the example. Okay, so subtree XOR, let's say this is your tree. Okay, same, I mark these only. Okay, 0 1 3 4 and 2. Okay, so here I just give the values 5 6 7 8 9. Okay, so now here I am cutting what? I'm cutting 1 to 3. Okay, that simply means I'm cutting this 3. Okay, 1 to 3, 1 to 3. So I can say I'm cutting this 3. Okay, one parent is going to be this 3. Okay, for the new subtree, and for one is it is going to be 2. Okay, so here 3 means 3 and its parent. Okay, so 1 to 3, 1 is the parent, right? 3 and its parent. Okay, so here I'm cutting 1. Okay, so if I'm cutting here, so this is going to be one component. Okay, right? And here 2 means 2 and its parent, 2 and its parent 0. Okay, 0 2. So that simply means I'm cutting a 1 here. Okay, so let's say this is nothing but your A, and let's say this is nothing but your B. Okay, so A, this 3. Okay, so 3 is XOR value, you already know, right? XOR of subtree A. Okay, so it's nothing but 7 only, right? And XOR of B, just this part, right? So its value is nothing but 9. Okay, XOR of this let's say component 1, component 2, and component 3, very easy. Total XOR is nothing but total XOR, here 5 XOR 6 XOR 7 XOR 8 XOR 9 is nothing but 5. Okay, so here total XOR 5, and just do the XOR with XOR this component, so 7 XOR 9. Okay, so what you are going to get here? Okay, so what you are going to get now? 7 XOR 9 if you do. Okay, so 7, if I want to write in binary form, 1 2 4. I think I did some calculation somewhere, and then okay, let me do it again. Okay, so let's say this 7 you are going to write in binary form like this. Okay, 7 7 4 5 6 7. Okay, and 9 you are going to write it like this. Okay, 1 1 here, 0 0. Okay, so this is nothing but 0 1 1 and 1. Okay, like this. Clear? Okay, so this is nothing but 7 XOR 9. Okay, now with 5 you have to do now. So 5 you are going to write like this: 1 1 here, 0 0. Okay, so this is nothing but 5. Okay, so now if you do 1 1 and here 0 and here 1. Okay, so what is the output? 1 2 4 8. Okay, so 8 10 11. Okay, so this output is 11, right? So let's see if 11 is correct, okay, or not. So 11 means for this part. Okay, for this part. So this part, if you see, we have 5 XOR 6. Okay, 5 XOR 6 we already know. What is 5 XOR 6? How can I maximize? Okay, see here, 5 XOR 6, and then I have to do with 8. Okay, 1 second here, I just need to move the space here. Okay, so 5 XOR 6 you already know, that is nothing but 3. Okay, here 3, and 3 how you going to write in binary form? 0 0 1 1. Okay, 1 2 4 8. Okay, and 8 how you're going to write in binary form? 1 0 0. Okay, so this is nothing but 1 0 1 1, that is nothing but 11. Okay, that is correct. Okay, so now if I just minimize the screen, all right, and just I shift to this side. Okay, so I'm getting 11. Okay, of 5 6 8, right? I'm getting 11, right? And here with this formula also, okay, total XOR 5 and 7 9, I'm getting 11. Okay, so this is correct. Okay, I validated. So for disjoint cuts, okay, disjoint cut means two edges you cut are not on the same root to leaf path. Okay, clear, done. This is part one. Okay, now nested subtrees means one inside another. Okay, so now what does this mean? Let me just maximize the screen again. Okay, so here one cut is inside the subtree formed by the other cut. Okay, meaning one edge is closer to the root and the second edge is inside that first subtree. Okay, so here again, root to leaf, there is one path. Okay, so you are going to do first cut here. Okay, so this you can say this is nothing but outer cut, outer cut. Okay, so now this is one part. Okay, and this 0 2 is one part. Okay, right? So now inside this subtree also, if you cut it here, okay, so this you are going to say inner cut, inner cut. Okay, so now you have trees like this, 0 to 2. Okay, then here 1. Okay, this was the case 1 3 4, but you now make one more cut. Okay, so now you have 3 here and here like this. Okay, so now if you see this, right, so here 0 1 1 cut, here you are going to say it outer cut. Okay, so with one cut you are making 1 as parent. Okay, and with other cut you are making this 3 as parent. Okay, so these are the two nodes I'm picking. Okay, right? Okay, 1 and 3. So 1 and 3, okay, I can say that this is nothing but one pair. Okay, 1 and 3 I'm checking right now. So this one I can say 1 and its parent. Okay, 1 and its parent. Okay, so I can say this is A. 3 means 3 and its parent, so I can say it B, or let's say B. Okay, so this is one component, this is one component, and this is one component. Okay, so now this little bit change, okay, to get the values of XOR. Okay, comp 1, comp 2, and comp 3. Okay, so here suppose A is the ancestor of B. Okay, so A means outer cut. Okay, right, and then 3 means inner cut. Okay, right, clear. A is outer cut, right? 1 and 3, so 1 and its parent. Okay, outer cut. Then we have this tree. Okay, so now inside this subtree we made one more cut, that simply means inner. Clear. Okay, 3 means 3 and its parent. Okay, so suppose a is nothing but 1, is the ancestor of B, right? So what you are going to do, comp 1 you can say what is the XOR of this B, you can simply say 7. Done. Okay, clear. All right. Okay, now next time, comp 2. Okay, comp 2, how you are going to calculate comp 2? So comp 2 is nothing but XOR of this complete subtree. Okay, this 1 3 and 4, what is the XOR of this complete? And among this complete I need to cancel out this part. Okay, so complete subtree, XOR of subtree A, that simply means this complete, and I need to subtract this, so I will just take the XOR of this. Okay, XOR of subtree B. So if that simply means outer minus inner. Okay, so here I can say 6, first this is 7, right, and this complete now XOR of subtree A is nothing but 6 XOR 7 XOR 8. Okay, and XOR of subtree B is nothing but 7 only, so I'm going to write like this. So this 7 and 7 is going to cancel out each other, so 6 XOR 8, so that is nothing but 14. Okay, and this 14 is correct. Okay, if you just take this part, okay, this white color only, okay, instead of using this formula, okay, this complete formula. So if you take this part now, so 6 XOR 8, so what you are going to get, so you are going to get here I've solved. Okay, 1 and 4, 6 and 8, 6 XOR 8 is also 14. That's it. Okay, and I think I did some calculations here, right? Here 6 and 8, it is nothing but 14. Clear. That's it. Okay, so now this is how I'm going to get the value of comp2. Now comp3 is very simple. Comp3 means one part, okay, one left out part, right? So one left out part and this, okay, so total XOR, okay, and this complete, okay. First we did this cut, right? 0 and 9, okay, and we first did this cut, okay, so this and complete, okay, so we will get this value, right? So total XOR with XOR of subtree A, okay, so that simply means total XOR is 5 we have, okay. Same example I pick here. I solved total XOR, and if you want to see 5 XOR 6 and XOR 7 XOR 8, you can pause the video and check this, okay. Here are the values, okay, 5 6 7 8, okay, clear. All right, okay, so now let me come here, right? So here this is how you're going to get the value of comp3, okay. 5 and XOR of subtree A, 6 XOR 7 XOR 8, so you're going to get 12 as the output, okay. So here you're going to get that, okay. So you can pre-calculate. I think I can calculate that as well somewhere, but I don't know where, but you are going to get 12, okay. So and this 12 is going to be right, okay. So you can say 9 and 5, okay. So if you do 5 and a 9, okay, this part now 5 and 9, so here I did 5 and 9, okay, so 12, that is correct, okay. So this is the formula for nested cuts, and this is the formula for disjoint cuts, okay. And I have explained the two possibilities when removing two edges, okay. This is just for one edge, okay. For with one edge, what is going to happen? We are going to make two components, okay, with two cuts, okay. Removing two edges splits the tree into three components, okay. So I hope that this is clear. All right, okay, this is done, okay. So now this is also done, you are clear with this, okay. So now here we must decide for two cuts edges whether their resulting subtrees are disjoint, no overlap, nested, one inside the other, okay. This changes how we compute the XOR of the components, okay. So now there is one more thing that matters here, okay. We are going to apply the DFS, right? So why entry and exit time works, okay. So let me just minimize the screen a little bit here, okay. Now come here, okay. So during a DFS on a tree, right? So when we enter a node, we are just going to mark entry, okay. In of node, time counter is going to be incremented. When we are going to exit a node after visiting all its children, we are going to mark out and a node, okay, out and node, right? So properties: a node A is the ancestor of node B if in time at A node is less than equal to in time at B node, okay. So that simply means that first we enter A and then we enter B, okay. And out time of B is first we exit the B and then we exit the A, okay. So if this is the condition, that simply means a node A is an ancestor of node B, okay. So I can prove this as well, okay. So this is the intuition. So let me just maximize screen here as well, okay. So in DFS, what we used to do, we used to do pre-order traversal, right? So in pre-order, first we go to mid, then we go to left, and then we go to right, clear. Okay, so now here see, okay, so here first you are going to go to 0, so in of 0 is 1, then mid, after that left, okay, this is the left, so in of 1 2, okay, so time counter incremented. Then you are going to go here, in of 3 3. Now no children for 3, you are going to out of this 3, okay. So let's say out of 3 is values 4, okay. Now you are going to go to this, okay, mid, left and right, okay. So in of 4 is 5, then exit 4, okay. So 4 6, so then exit 1, out of 1 is 7, then you are going to check 2, in of 2 is 8, then exit 2, then you are going to get 9, okay. Out of 0 is 10, okay. So now here check ancestor relation, is 1 is ancestor of 3, 1 is ancestor of 3. So in of 1 is 2 and in of 3 is 3, so 2 is less than equal to 3, and out of 3 is equal to 4, and out of 1 is equal to 7, okay. So yes, nested. 3 is ancestor of 2, so in of 3 is 3, 8 is less than equal to in of 2, which is 8, no, okay. So disjoint. So this is how this condition is going to help, okay, and I'm going to use it, okay. So I hope that you guys are clear with this part as well. That's it, okay. This is done. Now let me just maximize, okay. This is done. Now why we need this in XOR problem? Okay, so if one cut is ancestor of another, nested case formula. Okay, you already know this. If no ancestor relation, disjoint case formula. Simple, very simple. Okay, this is done. Now let's see how we are going to solve this problem, okay, with one example. Okay, this is my example. Okay, nums and edges given to us, you already know, okay, what we are doing in this example, right? So here if you see, first these are the input, okay, right, and edges. So here we are going to create one adjacency list. Okay, I have already shown you how we are going to create that. Okay, now this is, now we have to implement the DFS. Okay, let's see how DFS is going to work. Okay, let me just move to this side. Okay, so we are going to start from 0. Okay, so 0 is our root. All right, so from 0, in of 0 set it to 1. Now go to child. Okay, so 0's child is 1. Okay, so go to child 1. Okay, in of 1 mark it true, then 1 0, then you are going to move to 1. Okay, so one child is 0, we have already visited. Okay, 0 is parent, no need to visit. 2, okay, go to 2. Okay, in of 2 3. Okay, timer incremented. Okay, no more children of 3, so we are going to get the value of XOR of sub tree, that is nothing but 5 here, and then we are going to come out of this 2. Okay, so I'm making it 3. All right, so 0 to 1, and then 1 to 2 I go, no children, so I come back, I reach here 1. Okay, so now back to node 1. So XOR so far, so 5 this, okay, 5 of this. Okay, now from here we are returning 5. Okay, so 5 and 5. Okay, this 5 and this 5. So here back to node, XOR so far 5 XOR 5 0. Okay, we will continue because here for 1 3 is also one children, right? So we visit node 3. Okay, so for node 3, in of 3 I'm going to update 4. Okay, go to child 4, then visit node 4. In of 4 is 5, no children, XOR of sub tree 4 is 11. Now we come back here, 11 and 4, so XOR of this complete is you are going to do 11 XOR 4. Okay, so no children, so here you are returning 11. Okay, out of 4 5 done. Now you are going to back to node 3. So XOR now 4 XOR 11. Okay, for this complete, so 4 XOR 11 is 15. Now XOR at sub tree 3 is 15. Now you are going to come back, okay, out of 3, right? So you are going to again reach 1. Okay, and at 1 from here 5 is coming, from here 15 is coming, and for this one 5. Okay, so XOR 5. Okay, node 1, 5 from node 2 is coming, and 15 from node 3 is coming. Okay, so total XOR is going to be you are going to calculate, you are going to get 15. Okay, so out of 1 5. Okay, then you are going to back to node 0 here. XOR at node 0 is 1, and overall you are getting 15, so you are going to get 14. Okay, so XOR of sub tree at 0 is 14. Okay, this is total XOR, and out of 0 is 5. Okay, so in the end you are going to get your sub tree XORs like this. Okay, for all the nodes 0 1 2 3 4, you are going to get entry and exit time as well. Okay, done. Okay, done. This is done. All right. Okay, so now once this is done, okay, then after that what you need to do? Okay, so then after that you have to check all the pairs I of j. Okay, so now here you are starting from root. Okay, right, now let me show you why we are looping over the nodes 1 to n minus 1. Okay, 1 to 4 we have to root. Okay, so 3 is rooted at 0, so we have to check the pairs, right? XOR of subtree I is nothing but, when I say XOR of subtree I, that is nothing but XOR of the subtree rooted at node I. Okay, so if you cut the edge between I and its parent, clear? So considering node I is same as considering cutting the edge parent of I to I. Okay, so that is why we are starting from here, because there is no parent. Okay, for 0 no parent. Okay, so 1. So now here we have to check all the pairs. Okay, we have to check all the possibilities. So I can, maybe I can cut 1 and 2. Okay, 1 and 2 means 1's parent 0. Okay, so that means this cut, and 1 means parent of 1, that is 0 to 1. Okay, this 2 nothing but parent of 2, that is nothing but 1 and 2. Okay, so this, so if I cut this, right, so I have to check then if 1 is ancestor of b. I have to check all possibilities, 1 2 1 3 1 4, then 2 3 2 4 3 4. Okay, I have to check all the possibilities. Okay, these are the nodes, so I have to check is 1 ancestor of 2. Okay, so I have to, if it is yes, then I have to apply the formula. I have to get the score. So pair 1 3 I have to check, then pair 1 4 I have to check. Okay, if nested. Okay, if nested, if not this not in this nested disjoint, then this. Okay, this you are going to get this. Okay, so minimum score across all the pairs, you are going to get something like this, right? and you have to turn the minimum among them. This is minimum. Okay, so you have to turn that. Right, so here this is your tree. So pair 1 2 means cut edge parent of 1 0 to 1. Okay, as to node 1 as to node 2. Okay, so this is the meaning of this. Right, so here each node except root corresponds to one possible cut edge. Okay, edge containing node, so it's parent. Okay, by checking all pairs of node ing, we effectively check all the pair of edge cuts. All right, so I hope that you guys are clear. Okay, so that's it. Okay, this is the explanation. Okay, so it still took 30 minutes after doing a lot of this pre-work, right? So if I have to do the pre-work during the video itself, okay, like writing everything, then definitely it's going to take a lot of time, right? It still took 30 minutes even though I write all these stuffs previously, right? All these, right? This and this part I already written. Okay, but still it took 30 minutes. Okay, now let's write the code. The code is very simple. Okay, whatever I explained, I'm going to do the same thing, nothing complex. All right, so first thing here you need to do, just create one arrays, right? So XOR subtrees in and out. Okay, time counter, you have to do all this. All right, so here int XOR, and here you can say sub tree. Okay, and then here you can take int in and out for all the nodes we need, right? And here time counter you can start. Okay, time is equal to 0, and here list. Okay, and here you have to take integer, and here graph. Okay, this is done. All right, and here take total XOR x capital. Done. Okay, so x capital XOR, now it looks good, and or you can keep it small. All right, so this is done. Now here very simple, so here just calculate the length of nums array first. What you have, nums dot length, and then here just initialize the arrays and all stuff. Okay, sub tree, okay, is equal to new int, and here just pass n. Okay, done. And then in is equal to, here also you can just copy this new int n, and here out is nothing but new int n, and you have to create adjacency graph as well. Okay, array list. So here you are going to do create one graph. Okay, list integer. Okay, graph, just initialize it. Graph is equal to new array list, and here just pass n. That's it. Okay, now after that you have to just iterate over all the nodes. Okay, int I is equal to 0, I is less than n, I plus plus. Okay, so now for all the nodes, okay, you have to add the edges, right? So what you need to do first, let's just create the array list for all the nodes. Okay, so graph of I is equal to add this node. Okay, this is the array list. Okay, in the array list I will add the values. Okay, so what I'm going to do, I'm just going to do, I have drawn somewhere here, I think. Okay, maybe, yeah, here. Okay, so this is 0. Okay, from 0 we can go 1, from 1 we go to 0 to 3. Okay, I will just add all this stuff. All right, so here this is how I'm just going to do this, and here just iterate over all the edges for int e in the edges. Okay, you are using for each loop. Okay, so graph. Okay, graph, and here e of 0. Okay, done. Here you are just going to add e of 1. Okay, this is done. All right, same way here graph. All right, and here you are just going to pass the value at this index. Okay, e of 1. Okay, whatever the value at e1. Okay, so in this you are just going to add the value which is available at e of 0. Okay, this is done. So now this is done. Okay, now after that what you need to do, you have to compute the XOR and timings. Okay, so here just create one total XOR variable. Okay, we have already created that, so just here just going to call this DFS. In the DFS just pass 0. Okay, starting from here. Okay, parent of this root is -1, and here just pass nums. Okay, so what you are passing here in DFS, you are passing the node, you are passing the parent, okay, and nums array. Done. Okay, this is we are going to get total XOR from here, let's say. Okay, and then in the answer we need min value in the end. Okay, so here initially I'm just going to add the max value of integer. Okay, so integer dot max underscore value. Done. And then we have to check all the pair of nodes, okay, treated as edge cuts. All right, so here for int I is equal to 1, I is less than n, here I plus plus. All right, now inside this one more loop for int j is equal to I plus 1, j is less than n, and here j plus plus. All right, and inside this what you need to do, you have to just update the answer as math dot min. Okay, you need min, right? Math dot min. Here just pass the answer, and here you are just going to calculate, call one variable calculate score. Okay, so calculate score, you are just going to pass the different pairs. Okay, so I and j. Done. Okay, this is done. So in the end from here you are simply going to return answer. That's it, return answer. Now I'm going to write a very simple DFS. Okay, so here I'm just going to write DFS to compute the subtree XOR and time in and outs. Okay, so here private int DFS, and here just I'm going to pass the node, I'm going to pass the parent, and I'm just going to pass the nums. All right, and here in, okay, in at node, here I'm just going to do plus plus time. Okay, and here int XOR is equal to nums of node. Okay, and here you have to just iterate over all the neighbors. Okay, int nei is equal to graph, and here node. Okay, just iterate over all the nodes, right, for that particular neighbor. Okay, and if that neighbor, we have already visited that parent. Okay, if neighbor is equal to parent, right, so in that case just continue. Okay, and otherwise here just we are just going to operate the XOR. Okay, so XOR is nothing but XOR is equal to, here you are just going to call the DFS. Now you are going to call the DFS on the neighbor. Okay, right, so 0 to 1, and then once adjacency list you are going to check, now definitely 0 will be there, so you don't need to check the parent. Okay, again you have to just continue. Okay, skip that. So node, and here nums. Done. Okay, all right, so this is done. Okay, let me write it like this. Okay, now it's more clear. All right, now it looks good. Okay, this is done. Now here you are going to calculate the XOR. Okay, and once you calculate the XOR, okay, of that particular node from all the children, okay, then you are just going to update the XOR of sub tree. Okay, XOR of sub tree of that node is nothing but is equal to value of XOR. Done. And then just update the out of that node. Okay, is equal to time. All right, and then return of this XOR. Okay, this is done. All right, so this is how you are going to write the DFS. Okay, this is done. Then after that we have to check if an A is an ancestor of B using in and out times. Okay, so that formula you already know. Private boolean is ancestor. Okay, and here int A and int B. Okay, so here you have to just return in of A is less than equal to in of B. Okay, and here and out of B. Okay, it should be smaller than the out of A, right? So out of A, this is done. Okay, so this is how we are just going to write is ancestor method. Now here how we calculate the score, so for that I'm just going to write, okay, calculate score. Okay, so in this we are just going to pass the pair values. Okay, int A, let's say, and int B, right? So now for this we have to calculate. Okay, so here let's say we have three components. Okay, x1 and x2 and x3. Okay, so now here I'm just going to check if is ancestor, okay, if is ancestor a comma b, I'm going to pass. Okay, so if that simply means b inside a, I can say, right? Okay, so x1 I'm just going to calculate xor sub tree. Okay, and here I'm just going to pass b, right? Okay, say this is for x1. Okay, now I have to calculate the x2. So how I'm going to do that? X2 is nothing but xor of sub tree a, and here with XOR with nothing but XOR of subtree b. So I can simply copy this and I can paste it here. Okay, done. And x3 for this component, so total XOR which we have, total XOR. Okay, and here I'm just going to write XOR of subtree a. Okay, so this you already know how we are writing. Okay, clear? This is done. Now here as if, okay, maybe is ancestor. Okay, maybe b is inside a, right? A is inside b, right? So in that case, here I'm saying that a inside b. Okay, so in that case, again you have to just simply copy this, okay, and paste it here. Okay, now x1 is XOR subtree. Here a you have to write, here same you have to write a or b, okay, whatever you want, b and a, it will not get any impact. Okay, and here total XOR, and here you have to write XOR of subtree b. Okay, this is done. And in the else part, that simply means I'm talking about disjoint. All right, so in this case what you need to do, so here just simply copy this, paste it here, XOR of subtree a, here XOR of subtree b. Okay, and here total XOR of subtree, here just copy this, okay, XOR of subtree a, let's say, and here XOR with XOR of subtree b. That's it. Okay, this is done. So this is how you're going to calculate. Okay, and once this is done, then here you have to return the maxwell minus meanwhile, right? So how you're going to get the maxwell first? So maxwell among the max of x1, x2, x3, and meanwhile means mean of x1, x2, x3. Okay, so here you're just going to write math dot max of x1 comma math dot max of x2 comma x3. Okay, this is done. And same way here you are going to update, you're going to write the meanwhile. Okay, so meanwhile is nothing but math dot mean of x1, and here math dot mean of x2 comma x3. Okay, once this is done, now from here you have to simply return max value minus mean value. Okay, mean value, done, right? So now let me just format the code and let's run it and see if there are any code issues. We'll try to fix that. So yes, there are some issues, so let's fix that. So here graph spelling mistake. Okay, now let me run it again and see. So yes, there is one more issue. So here XOR subtree, and here, okay, so here s should be capital only, tree small. Okay, tree I'm taking small everywhere. Let's see. Okay, so here, okay, everywhere I'm taking small only, I think. Okay, here also I'm taking small only. Okay, so just let me just copy this and replace it with the what we need XOR sub and t we need small. Okay, so replace all I can do. Okay, now let me run it again and let's see. Okay, so all the test cases has been accepted, right? Now let's submit it. Okay, so see, our solution is accepted, right? So I hope that you guys are able to understand today's problem, and if you guys still have any doubts, then please feel free to ask in comment section. Till then, keep coding and keep practicing. Thank you, bye bye.